one of these. Carbons here, we only have one, yeah? But we have 4 hydrogens, so that means we need 2 of these. When we add it up, that means on the oxygen we need 2 and 2 or 4 oxygen. That make sense? Is it balanced now? Oh, what? 2 oxygens. See, I make mistakes on purpose. You see if people are paying attention. 2 O2. Alrighty, now is it balanced? Okay? Now, once again, every time we want a mole of oxygen, we have to add in 3.76 moles of nitrogen. We can't just add in the oxygen pure because we have air. So, in general, for every mole that we want, or every molecule of CH4, if we want an exact balance here, we have to add 4.76 moles of air. Now, what if we don't have an exact balance? What if we don't have enough air? What happens to some of the fuel? Doesn't burn, it's wasted, yeah? On the other hand, if we have not enough fuel, what happens? Too much air, we have leftover air, we didn't take it to full advantage. Does that make sense to everybody? By the way, that's half the magic of an automobile, getting the air-fuel ratio right. By the way, also, in terms of volume, we have 4.4 times in terms of moles. Let's convert that into mass. How do you convert moles to mass? Anybody remember? You want mass ratios? Who's the chemist? Use the molecular weights. Remember that? So we can say that basically for every mole of CH4, that would imply perhaps CH4 has an atomic weight of 16. We'll have 16 mass units. That could be kilograms, that could be grams. Compared to air, which has a molecular weight of 20, and that I have to look up. It's either 28 or 29, and I wrote it down. There it is, 29. All right, so now let's add it up. We want to do this reaction. Let's suppose we put in 16 kilograms, or grams, let's use grams, of CH4. How much do we have to add of air? 2 times 4.76 times 29. So let's, who's got the calculator? You guys haven't learned yet. As engineers, you're supposed to have that thing at the ready, right there, on the hip. You never know when you're going to need to whip it out. You got it? So what's our ratio of fuel to air, or the fuel-air ratio, if we have 16 grams compared to that many grams? Who's got? You got a number?
I had a number.
Okay. It's gone. I have the number. 0.058.
Yeah. That's what I was about to say.
Or an air-fuel ratio of 17.2 to 1. So, what's the problem if you want to get a high performance? Supplying a lot of fuel or supplying a lot of air?
Air.
Air. For your project, it's really just getting the proper mix. But for an automobile, if you want to have a high-performance automobile, what's the key problem? Getting a lot of air into the engine. What does a turbocharger do? Pumps air, right? It's a compressor that pumps a lot of air. You can always add enough fuel. Getting air in there is the hard part. So anyway, I digress. Where are you going to learn all this stuff? So that you can do it for gasoline and diesel and biodiesel and all the rest of the stuff. Thermodynamics, which you guys will be taking next year. Later on, you might take an advanced thermal course. I think we have one that we call Advanced Topics. You can also, in the aerospace option, take propulsion. We still have that, don't we, Diana?
Yes.
Propulsion.
What about fuel cell technology?
That wouldn't be combustion,
Okay.
but internal combustion engines would be in the auto option. And of course, you can go much beyond the simple stuff. You know, combinations of fuel. More importantly, you can take a fuel. You can take a C84, and just from the formula, you can figure out how much energy it should release when you burn it. Okay? A little more advanced thermal chemistry. Either as a grad student you can do that, or perhaps over in the chemistry department. All right, so let's get a little bit away from the actual combustion process and talk about what happens with the combustion. Whoa. Whoa. I'm losing it. I thought we tightened that thing.
I did. Okay.
I thought I did.
Sorry.
Maybe that was the piece that fell off.
Fell off.
So let's talk about what happens in that chamber and why it's important. So here's the chamber. It's a very rough schematic. Here's the barrel. There's your potato stuffed in there. We'll talk a little bit about why you want to stuff it in. So in here we have our air and our fuel. And we give it a little spark. And it starts burning. And actually when you take internal combustion engines or propulsion, you will discover that the burning itself is not instantaneous. It's not an explosion. It's a burn. And it actually goes from the spark and spreads out in waves until it eventually gets through the whole combustion chamber. It's a flame. And the study of the flame front is one of the real topics in mechanical engineering because it relates to pollution formation and efficiency of the engines and all of that stuff. But anyway, as this burns, it releases heat, yes? So what's going to happen? The temperature is going to go up. So we're going to start increasing the temperature of that gas. You guys are taking physics and chemistry. What do we know about how an ideal gas reactor behaves? Anybody remember that? How about pressure times volume is mRT? Or some variant on that, yes? You guys like that? That equation? Have you seen it before? Okay. In here, do we have a fixed amount of mass? Yeah, and it's mostly air, but some other gases. So the mass is fixed. Well, let's solve for the mass. It's PV over RT. R is a constant. The volume is not quite constant because the potato is going to just start to move. But it's going to be a small change in volume compared to everything else. So as the temperature goes up, if you're going to maintain this ratio constant, what has the pressure have to do? Increase. Yeah? So we're going to get increasing heat. Obviously, what is that going to do? That's the whole basis. Here's your potato. Here's the tube. You're going to have a high pressure on this side a low pressure. That gives you a net what? Unbalanced force. Next year, in dynamics, we will be looking at net unbalanced forces. And what we will do is Newton's law, yes? Sum of the forces, mass times acceleration. Yes? You guys remember that stuff? Yeah. So, we have unbalanced forces in this direction. What's it going to do? Accelerate. Now, the subtleties behind that. The subtleties. What if the force is changing as